Okay, we are recording right now. The recording of the video capture software will have my picture at the lower right. I'm gonna try to share my screen, my video again, and let's see what happens. Yeah, see, Zoom doesn't let me share my camera simultaneously with the other software. I didn't used to have this problem. But let's go ahead. I'm going to close this thing here. Let me get my notes, lecture note. Here's the lecture notes. I'm going to close this guy, save it. I'm going to close this guy, don't need anymore, save it. Lab notes, we don't need the lab notes. And what? Those are the notes for that last chapter. 25th was yesterday. Okay. I'm gonna put it here 26. Insert. That's July 26, 21. So what you're going to do, you're going to do this one right in here. Do this one right in here. Motion of charges on uniform field. Hopefully we did electrostatic equilibrium. I think I'm going to skip this one. Maybe we don't need that. Here you go. But let's do this one here. This one is kind of an easy type. It's just like what you have right in here. Motion of charges on uniform field. It has applications in gas discharge lamps. No, not in gas discharge lamps. It has applications in Crookes tube. This one here. Not necessarily gas discharge. Yeah, it has. Yeah, it has. Has applications on those devices here. Gas discharge lamps, Geisler tube, Crookes tubes, and CRTs. We still have gas discharge lamps nowadays. You know, those neon signs that those neon signs that you see out there are gas discharge lamps. We still use those. This thing was invented, some time ago. But let's talk about that. I'm gonna show you here the book, okay, and how we generate a uniform electric field. It's possible to generate a uniform electric field. What we can do, we can get two plates, flat plates, just like is illustrated right in here, connected one plate to one terminal of the battery, the other plate to the terminal of another battery. Here you go. Here's my battery. Here's my battery. You cannot see it, right, in my Zoom. But I have a 9-volt battery here with me. I can get a metal plate, connect one end to the negative of the battery, the other end to the positive of the battery. When you do that, you have this distribution of charges in the plate, and at the end and now that you have a distribution of charges in the plate, you create an electric field. And the electric field that you create is a uniform electric field. What does it mean, uniform electric field? Uniform electric field means that the electric field has the same value everywhere within this volume. That's what it means by having a uniform electric field. Okay, so let's go ahead. First, how you create a uniform electric field. Okay, we do the following. Get two metal plates. Can be circular, can be a rectangle, can be either circular or square. Can be circular, square, or rectangular. And connect one plate to the negative terminal of a battery and the other plate to the positive terminal of a battery. When you do that, you know. So what happens when you, here you go, one, when you connect the first plate to the negative terminal of the battery, you generate a distribution of negative charges in that plate. Okay? When you connect the second plate to the positive terminal of the battery, you generate a distribution of positive charges in that plate. Now that you have a distribution of positive and negative charges separately, right? Each charge is going to generate, each plate will generate its own electric field, which will superimpose with one another, and which will superimpose with each other and reinforce. Okay? That's what's going to happen. And then the resulting field between the plates will be a uniform one. Just like you see here, represented by those lines, those straight lines. Here's a three-dimensional representation of the field. What you see right here, this cone is just what appears like a cone is in reality the arrow of your field lines, the invisible field lines. One charge is positively, one plate is positively charged, the other plate is negatively charged. Okay? So, what else do we know? What else do we know? We know it's possible to calculate that. I still didn't show you how to do that. It is possible to calculate that the electric field between those plates is going to be given by the charge divided by the area divided by this constant. This constant depends on that K constant that you saw before. Okay? Here, remember this guy's K is 9 times 10 to the 9. And then there we have that unit, Newton meter square per Coulomb square. Okay? The epsilon naught is called the permittivity of vacuum. It is possible, here we go. It is possible to calculate the electric field between these two plates. We are not going to do that here now. We are not going to do that here now. Okay? Which is given by, here we go, let's write it down. Because it's uniform. Okay, remember the electric field is going to be proportional to the amount of charge. Remember that? Okay? Point charge also, right? The electric field is directly proportional to the amount of charge. But because it's a uniform electric field, you know, the field is not going to vary the distance. And we have that constant epsilon naught right in here. Go. Going back, right? Let's, yeah, epsilon naught. Here's the value of epsilon naught. I'm going to copy, and this is called the permittivity epsilon naught. Epsilon naught is called the permittivity constant of vacuum. Epsilon naught is called the permittivity constant of the vacuum, and is given by, I'm going to need that for your problems, right? For your homework. Here you go. I'm going to copy and paste that to my notes so that everything is documented there. Here you go, like that. Make my life easier so I don't have to type everything from scratch. You don't need to memorize that. Okay, but you should know that it's a constant and it is inversely proportional to the K constant. This guy is like 9 times 10 to minus 9 times 10 to the 9, right? 4 pi is around 12. 12 times 9 is going to be what? 12 times 9 is going to be almost 100, right? So what was 10 times 10 to times 9 becomes 10 to the 9 here downstairs, become 10 to 11 here. Okay, when we divide that, you get this number. So the direction is perpendicular and it starts at the positive, ends at the negative charge. Remember, positive charges are a source of fields, electric fields. Negative charges are a sink of electric fields. You also saw that there is a force, there's a relationship between the force and the electric field, which is the charge that's subjected to the field times the field itself. Okay, so let's write it down. So suppose that we put an electric charge here in between those two plates. Suppose that we put an electric charge between those two plates. Let's write that down. Suppose we place an electric charge, lowercase q, between these two plates. Outside the plate, the electric field is 0. Okay, let's write that down here. It's possible to calculate between these two plates. We're not going to do that, which is given by, okay, outside, here you go, outside these two plates, the electric field is negligible. Okay. Suppose we place an electric charge Q between these two plates. Picture that, getting an electric charge placed right here. Let me see if I have a better slide for that. I'm gonna get that from my PowerPoint. Here you go. Illustrations, P38. P38, yeah, this one here I should have right here. Let's see. So we can have a picture. Point charges. Oh yeah, here you go. Okay. Here you go. If you have just one plate, I'd like to show that to you, okay? If you have just one plate positively charged, and here's this positive charge, okay? This means electric charge is 0. So you have electric fields coming out in both directions, to the right or to the left, okay? And if you have just a plate with a negative electric charge, you have electric fields coming into the plate, right? Sink and source. Source is the positive plate, positive charge. Sink is a negative electric charge. So you have a bunch of electric charges distributed here. The distribution is uniform. And they all produce this electric field that you see right here, a uniform electric field. When you combine the positive with the negative, separate by a given distance, what's happening? The blue plate is going to produce an electric field to the left, and the red plate is also going to produce an electric field to the left. That's what I mean that they superimpose to one another. That's what I mean that they reinforce each other in this volume, okay? In this volume only. Outside the volume, what's happening? The electric field from the positive plate cancels out with the electric field of the negative plate. See that? We are assuming that this distance here is very small. That's what we are assuming. So it is an approximation when I say that when the electric field cancels out is zero. It is an approximation. It happens both on the left side as well in the right side. Okay? Here you go. I'm showing the electric field being superimposed here. Now the electric field outside is zero. Here you go. Now the whole arrow there inside. Step by step. The book doesn't show you that. The book doesn't show you that. Now if I put an electric charge here, a free electric charge within this volume, is air, okay? Or vacuum. It can be air or it can be vacuum. Okay? What's going to happen to this positive charge? This positive charge is going to be repelled by this positive charge distribution right in here. And it's going to be attracted by this negative plate. Can you picture that? Okay? That's the step by step that you have to know, that the book doesn't show. So here you go. We have this force applied to this charge. And the charge is going to move with an acceleration. This charge has a mass, okay? Let me put that a charge with a mass as well. I'm going to repeat that. Here you go. This one like that. I'm going to repeat this one, and then charge with a given mass. I'm using in lowercase q. Oh gosh, this guy keep on doing that. And mass. I'm using a positive charge. Okay. Sigma means here that is a q, right? I'm gonna put uppercase q. Sigma is related to q. Sigma is q divided by the area of this plate. Here you go. That's what we have. So here you go. In the next slide, you're going to have this force. Okay. Let me copy this guy and paste in the next one. Yeah. Because we have a force, I gotta put a force here, right? Force symbol. Force symbol for this arrow. And this force is going to generate an acceleration for this charge that's going to move between each plate. That's the type of motion we are talking about. Is a repulsive force due to the positive charge, is an attractive force due to the negative plate. But you can also picture that as an electric field propelling the charge. Let's do that. Here you go. I'm going to copy this one here. I'm going to do that in a different way. Here you go. I'm not going to, my charge, I'm going to erase this guy from here. That's the next step. Okay. Here's the electric field, okay? Here's the electric field. This electric field generates a force, right? Applies a force to the charge that's here inside. gonna become a little bit complicated, right? But let's do it anyway. So you can see the electric field superimposed to the force. And I'm gonna even change the color of my force. I'm gonna put like in red color. Here you go. And the acceleration, I'm gonna put it in this color right in here. So that we are going to come up with the equation of motion for discharge. That's what we are going to do. The force is going to be, here you go, Q times E. Q times E. Let me see if I have any questions so far. Feel free to interrupt me to ask any questions, okay? I'm sharing the screen, right? So, here we go. And that's what we have. Here we go, force equals Q times electric field. And then I'm gonna put in my, suppose we place an electric charge Q between these two plates, comma, the force applied, the electric force applied to the charge. Electric force applied to the charge is, you know, Q times E. And don't forget it's a vector, right? That's what that bold face there in your book is all about, is to vector and vector. Okay. So here you go. Q. Just to emphasize that you have Q here and you have E here. That's E. The E in the case of my drawing is going to be on the negative X direction. Oh, wait a minute. Let's do it. Yeah, I'm putting on the negative X direction. Okay? Because the X axis is from the left to the right. Let's do that. I'm going to put X. Since it's a vectorial equation, I gotta put everything in vectors. And then go negative right in here. So what do we wanna do? I want to find out the equation of motion of my charge, given the parameters above. You know, Q, big Q, big Q, Q, lower Q, big Q, A, and epsilon naught, that's known as well the mass of the charge. Okay? Mass of the charge. So how do? You apply, assuming all other forces are negligible, all other forces are negligible, and they are, like a force of gravity, right? We can find out the equation of motion, of the charge using Newton's second law of motion. Okay, net force is equal to mass times acceleration. Net force is mass times acceleration. you go. Mass times acceleration is charge times the electric field. We get that stuff. Here you go. The first thing that we get is the acceleration of the charge, which ends up being Q over M, the ratio of the electric charge, of the mass and electric charge. The acceleration is to the left. Let me put this negative sign right in here, right? I'm doing according to my PowerPoint slide. Okay? Have you seen anything like that before? Constant acceleration, you know? Constant uniform force, okay? This type of motion, here you go, is analogous to the motion of a free fall particle, to the motion of a free fall, to the motion of a particle undergoing free fall. Constant, constant acceleration. Constant slash uniform acceleration. Okay? And if it's constant slash uniform acceleration, then you already know what's going to happen, right? For the velocity. The velocity implying, meaning that the velocity is going to increase. The speed, not the velocity, but the speed, right, is going to increase linearly, and linearly with time, and the position will vary with in a quadratic fashion. Okay, so here we go. Velocity. Velocity, here you go, the equation for the velocity is like that. Velocity is initial velocity plus AT. V naught plus AT. A is this thing here, right? Along the x-axis, so you got and the position, you already know the position, right? It's going to be the x. We're going to get, it's one-dimensional motion, so we don't need to use vectors anymore. X naught, V naught, V naught T, V naught T plus half AT squared. So it's just what we saw before in mechanics. Motion along the x-axis. I can go ahead and put the A right in here, right? The V naught is 0 because the charge was put there in my plate at rest. The x naught is going to depend how I set up my axis. I see how do I set up. If I put my origin right in here, then the x naught is going to be this position here in the axis. V naught is equal to 0. And the acceleration is this value right in here. Right in that, like that. what you see here, Q divided by A, is the sigma that you saw there in my equation, okay, in my slide. Here you go, this sigma here. The sigma is Q divided by A. So here you go. So what's the applications for that? You know, well, the applications for that is for electron beam. Remember I told you about the Crookes tube? I told you about the CRT. Before the CRT was invented, we had to invent the other stuff, right? First, we have to invent the gas discharge lamps. And then technology advanced, and people, it was just a matter of making a more perfect vacuum inside that glass tube that we have. First, they invented the gas discharge lamps. That's how it goes. The first electrical light source in the history of mankind was the gas discharge lamps, or the arc lamp. Okay? Then they came up with the Geisler tube. Okay? And they start to see something that they couldn't quite explain. It was just a matter of being able to extract more and more, to make a more and more perfect vacuum inside that tube. Okay? The thing that they were looking, was like a dark shadow, like a beam of a dark shadow in that gas inside the glass tube. It's all explained in Wikipedia, in the Wikipedia. It's a really nice story that's in there. And then we had the Crookes. We had the gas discharge tube, we had the arc lamp, we had then the Geisler tube. The Geisler tube was basically this part here of what you see in this drawing, okay? You have here a heated filament producing electrons. We call them thermoelectrons. And then we have an electric field between those two plates that you see, the cathode and anode, okay? See, this thing is basically a circular plate. A circular plate that produces an electric field, a uniform electric field between those 2 points. So the electrons are emitted from this filament. There is a hole, right, on those plates. You still have a uniform electric field between those 2 plates. The uniform electric field accelerates the electrons. The second plate has a hole as well. So what you see here is what we call the Crookes tube. The Geisler and Crookes tube. The difference between the Geisler tube and the Crookes tube is that the Crookes tube is more advanced. It's a more advanced device. Why is it more advanced? That's because it has a better vacuum there inside. That's the difference between the Geisler tube and the Crookes tube. Once you get a better vacuum there inside, now your electron beams, your electrons that move here, can move a very large distance inside the tube. How did they find out that there was some sort of cathode ray? Okay, remember, that was before the cathode ray tube, right? What you see here is the whole thing that you see here is a cathode ray tube. But what you see right in here only is the Crookes tube. The Crookes tube would end right in here. At the time, the glasses that they produced was not a perfect glass. It was a glass that had impurities in there. It was a glass that had sources of phosphorescent sources or fluorescent sources, just like it's written here. Okay? And when the electron would impact the end of the Crookes tube, they would see that fluorescence, that greenish fluorescence that you saw in the video. And then they start thinking, why do you see that greenish glow, right? They start thinking, oh, that must be because there we have some sort of rays in there. And then they came, and because those rays were coming from what they would call a cathode part of the tube, they would call that cathode rays, not anodic rays. They would call it cathode rays. Eventually, they discovered that those rays were in reality particles, electron particles. And then the whole thing advanced, They start to add components to the Crookes tube. Okay? They put 2 additional plates, charged plates here in the vertical direction. Do you see that? Just like those plates that I showed to you in my drawing. Why did they do that? Oh, they did that so they could steer the electrons along while they move along this plate. Those 2 plates. Okay, they could steer. This one would steer in the horizontal direction, either to the left or to the right. Okay? Why they would want to do that? I'm going to tell you why very soon. And then they would put another pair of plates in the vertical direction. Why they would do that? Because now they would have the capability of steering the electrons in the vertical direction. Just by controlling the amount of electric charges on those 2 plates, here those plates would accelerate the electrons, just like you saw in the problem that I showed to you. And here those 2 plates would steer the electrons in the horizontal direction, horizontal deflection. And here these 2 plates would steer the electrons in the vertical direction. Why do you want to do that? There was a reason for that. You know, when you are painting a screen, you get your brush, right? And you paint your screen at different spots, right? With your brush. You get your brush, you know, put the ink there in the brush, and you paint your screen, your canvas at different spots. Okay? Here's the same thing. You have a screen. You have an electronic canvas coated with a fluorescent screen. If you can control the steering, the position where the trajectory of those the electron beam, you can start thinking how to paint a picture in this fluorescent screen. The moment that the electron impacts the screen, is going to produce maybe a greenish color, right? And if you are smart enough, you'll be able to paint a picture here in this screen with this electron beam. Provided, of course, you have the proper electronics to steer the electron very quickly, to steer the beam of electrons very quickly. That's why we solve this type of problem, so you can understand how the first televisions were made. The first televisions were made with this type of device, the cathode ray tube, that follow up from that was invented after the Crookes tube, which was invented after the Geissler tube, which was invented after the arc lamp, which was invented after the gas discharge lamp. Okay? So that's what we have here in this example. Let's do this example. Now you understood, right? How it goes. But before you go into the sample, I like this picture. You know, the only thing that I don't like about this picture is that there's too much information in there. The way I think they should have done that, they should have introduced the Crookes tube, only this part here, so students would understand that better. And then little by little, they would build up the whole thing until it gets to the cathode ray tube. Do you get the idea now, right? Yeah, the cathode ray tube was invented in 1897, but in order to get to the cathode ray tube in 1987, you had to have something else that was invented in the 1850s. And then finally, we had the first prototype of a television that was around the 1920s. You know, and you know that television screens and computer screens, they initially were that bulky device. Why are they this bulky device? Because they have this huge cathode tube in there to accelerate the electrons and paint the screen. Later on, some of you have seen that before, right? Those cathode ray, the TV with cathode ray tubes. Later on, people invented the LCD screen, and they invent the LED screen, and then they invent, now we have the QLED screen. Okay? So that 353. Any questions about that? That's the story that goes behind, that's the application that goes behind all this thing that we're talking about. It has practical applications. It's not something out there that is a pie in the sky. That is just a exercise of imagination. No, it's not exercise of imagination. This has actual real life applications, everything that we're talking about. Now, what else? We are talking about an electric charge that was placed here in between those two plates, right? That's the electron gun. That's the one that accelerates the electrons. They start almost at rest. They're floating right here with a very small velocity, right? The filament floating those electrons with a very small velocity. They start moving here. When it reaches this region here with a cathode and an anode, negative and positive plates, the electrons are accelerated. That story already told you. That story already told you. What's next? After the electrons is accelerated, they go through that other two plates that you saw that steer the electron in the horizontal, that steer the electron in the vertical. And how does it work? Okay, it works like that. I will play the movie for you. We start with my charge right in here. Can be either positive or negative. Okay, for the sake of illustration, I am illustrating a positive charge. And this charge is moving towards this region of uniform electric field after it was accelerated by the first set of plates. Okay? When it gets into the region of uniform electric field, what's going to happen? It will be repelled by this electric charge distribution, the positive, and will be attracted by the negative charge distribution. The force again is going to be uniform, it's going to be constant because the field is uniform. And again, what we get? We get the same type of motion that we get for a projectile. It's going to be a parabolic motion within this field until the charge exits the electric field between the plates. Okay? So let me see if I have the next. I don't have it. Yeah, too bad. But I can play the movie for you, right? Let's play the movie. Here you go. Next. Okay, here you go. The charge is moving along its path in a parabolic fashion. Okay? Parabolic fashion. The velocity vector is tangent to the path, right? Here you go. Velocity vector tangent to the path. And this velocity vector is increasing in magnitude. Oh. Oh. Increase in magnitude. Because it's being accelerated, right? Just like a projectile in free space. Interesting. I don't know whether. Okay, let's keep on going. Next slide, right? Here you go. Particle here, particle there. Okay, next one, gonna be a little bit. So here you go. We have the capability of steering the electric charge between those two plates. Okay, velocity vector right in here. Increase the velocity. I'm gonna change the color so you can see it better. Here you go. Better, right? Just like it happens to a projectile. And then when it reaches here the end, the particle is moving at an angle. Okay? I don't understand why this guy is not. Oh, that's why. Here you go. Like that. Okay, here you go. It starts here, moving a straight line, enter the field, a force is exerted in the charge, and the trajectory is a parabolic one. We can come up with the equations of motion for this guy too, right? And what are the equations of motion? Along this y direction, the velocity component along the y direction is constant. Doesn't change because there is no force along the y direction, but there is a force along the x direction. Okay? And it's just what we saw in physics 120. Let's go there. That's the, here you go. It's the same equation, okay? The same acceleration, but the same equation is a different velocity vector. What if the initial velocity is perpendicular to the electric field? Okay? Well, the motion of the charge inside the uniform electric field will be analogous to that of a projectile in a uniform gravitational field. Okay? So how do we do that? Here you go, we can do like that. V naught plus AT, and now the initial velocity has only a y component. Okay, we have an initial velocity, but the initial velocity has a y component right in here. Change it to y. Okay. Like that. So we can break down this equation into x and y component. Just like we had for the, here you go, we get something like that, right? And then we have the other one. Don't forget to go y. I can put the origin of my y right in here. So let's put it like that to simplify everything. And then y is going to be y naught. Y naught is going to be 0. And that's going to be v naught t. V naught in this case is going to be positive. V naught, here you go, I'll get that. V naught t. Here should be v naught x, right? V naught x is better. No acceleration along the y direction. Motion of a projectile. 401, we have 20 more minutes to go. Okay, that's what you have. That's what you have. And now let's try to solve this example. A cathode ray tube, CRT, is used to accelerate electrons. So now you understand the difference, right? Between the cathode ray tube and the other one, the Crookes tube, right? The Crookes tube is just this little part here in the back. Two plates producing a uniform electric field. They call it this whole component here the electron gun. A source of electrons. It can be a heated filament, but it can be also that Tesla coil. Remember that Tesla coil that the guy showed in the video? It can be the Tesla coil as well. And then, you know, as the science progressed, people found out ways to steer the electron in the horizontal direction and vertical direction, so they can paint a picture here in the screen. And this thing is done at very quick rates. Okay, it's done at very quick rates. You can program, you can design devices to change the amount of charges on those two plates at very fast. Think about that. We're talking about industrial process. People, you know, improve that to an art. That's what they did with these cathode ray tubes. And now cathode ray tubes too bulky. Cathode ray tubes, you know, it's not convenient to carry around. So now we are abandoning the cathode ray tubes and we are using LCD screens. We are flat screens, right? We are using LED screens. We are using QLED screens. So here we go. Motion of a projectile. Plates, uniform electric fields are used to accelerate electric charges. Here you go, that's the application. Electric charges and steer them inside a cathode ray tube, which was used in the first television screen, the first TV, the so-called kinescope. Okay, so three components. Let's see. The cathode ray tube, the CRT, has the following components. One, a source of electrons. It can be a heated filament or a Tesla coil, right? Tesla coil. Two, an accelerating, let's see, two charged plates to accelerate the electrons, the electron gun. A pair of charged plates. A second pair of charged plates to steer the electrons in the horizontal direction. A third pair of charged plates to steer the electrons in the vertical direction. Okay, CRT has the following components. See what's the figure. See figure 16.39. See figure 16.39. A screen, a fluorescent screen, can be phosphorescent as well. Fluorescent / phosphorescent, there is slightly different screen. To paint a picture using the beam of electrons. Okay. Oh, very quick. Now let's go ahead and do this example. Cathode ray tube, electrons are heated. They are then accelerated by an electric field between the cathode and anode. Suppose an electron passes through the hole of the cathode, the velocity, let's see, past cathode, okay. So they already have some velocity here. You know, that's because of the thermal velocity. We're talking about thermal velocity here. 10 to the 5th meters per second. Okay? Think about this velocity. Okay? I'm going to put that here. Even better, I'm going to use this one here. My favorite software again. Here you go. CRT tube, right? CRT tube. Example 16.9. 16.9. Initial velocity of my electrons is, go back there, 10 to the 5th meters per second. Meters per second. You know, just be reminded of the velocity of the light. Is 300, 123 meters per second. We can count, you know, that's going to count here. That 1, 2, 3, 4, 5. Okay, it's 10 to the 8. Okay? 3 times 10 to the 8 meters per second. That's how fast the electron goes. Okay? Velocity of the light is that. Just for comparison, those electrons are moving very fast. We're talking about 100,000 meters, 100 kilometers per second, right? No, yeah, 100 kilometers per second. We're talking about 100 kilometers per second. 100 kilometers per second, folks, this is almost 100 miles per second. 100 kilometers per second is the velocity of our spaceships, space probes that we launched a long time ago. The Pioneer spacecraft is moving like that at this speed, maybe a little bit more now that's moving away from the solar system. Most likely the Voyager spacecraft are moving that fast as well. With respect to Earth, right? The speed of the Earth around the Sun is 30 kilometers per second. So this guy here is moving 100 kilometers per second. Mercury is moving even faster around the Sun because it's closer to the Sun. But let's go back. Running out of time, 10 more minutes to go. The electric field is uniform in the z direction. Okay, that's the z direction here. 1 times 10 to the 4th Newton per Coulomb. What is the acceleration of the electrons? If the anode and cathode are separated by 2 centimeters, the final velocity of the electron. Okay, let's do that. Electric field. Is that 10 to the 4th? Let's go back there. I have a bad memory. Here you go. 10 to the 4th. 10 to the 4th Newton per Coulomb. Right? Here you go. What's the acceleration of the electrons, right? You gotta go and get the mass of the electrons. What is the acceleration of an electron? Okay. We gotta go and get, mass of electron times acceleration of the electrons is equal to the charge of the electrons times the electric field. I'm gonna put Q, lowercase q. He's just asking, the magnitude, right? He's not asking the sign. Let's see if he got it. Yeah, well. That's the z direction, right? So the electrons will be accelerated along the z direction because this plate is positive. Gonna get the charge of the electrons. Here you go. So for the mass, you gotta get the mass of the electron as well. Right? Charge of the electron. Let's go get to the internet. I can look at here as well. Let's see. What's the charge of the electron? The distance is, yeah, here you go. No, here. 1.6 times 10 to minus 19. Okay, Q equal to 1.6 times 10 to minus 19 coulombs. Oh. The mass of the electron. What's the mass of the electron? Let's take a look. I'm not going to look at the solution because I'm going to do my own solution. Here you go, mass of the 9.1 times 10 to minus 31. 9.1 times 10 to minus 31 kilograms. Okay? So go ahead and substitute everything. QME. Here you go. I am going to get this guy in the same line here. Oops. Okay, and that was the acceleration that I'm getting here. 10 to the 15th. 1.7 times 10 to the 15th. Let's see if I can do better. Simplify here. Calculate. Yeah, I got it. It's 16 actually. I'm getting 16. No, something wrong here. He's using this n as a number. There's something wrong here. Okay. I know what I have to do. I must have defined n as a given number before. I guess that's what happened. Okay, so let's go ahead and let's see what's going on here. Calculate. Yeah, good. Now I got it. 1.75 10 to the 15. Let's not forget that's meters per second square, right? N prime is what? N prime is kilograms meter per second square. So when I substitute kilograms for that, I get that's the acceleration that the electrons are being subjected to. It's a huge number, folks. It's a huge number. And then we have to know the velocity at the end of that electron gun. That's what he's asking. Here you go. What is the acceleration of the electron if the node cathode is separated by 2 centimeters? What's the final velocity of the electron, right? So what you gotta do, you gotta use, you know the acceleration, you know the distance, right? So what you gotta use that equation of the v square, v naught square plus 2a delta x, or he's calling that d. The book is calling that d. 2 centimeters. He did call d. Let's take a, yeah, he's using the d. Okay? 0.02. D is equal to 0.02 meters. Let's make sure it's 0.02. Go back and forth. Yeah, 0.02 meters. Okay? Now substitute. Oh, I know the initial velocity is here. The initial velocity is right in here. You square a big number, you're gonna get an even bigger number. The acceleration is a big number 2, but don't forget you still have to take the square root, right? And the d is kind of a small number compared to everything else. Let's see if I can get it expanded. Yep, that's what I'm getting. And now I have to solve for v. Yep, let's go. Calculate. Oh, he didn't calculate. Oh, I hate that. Expand. Oh yeah, I got it. Now I got it. 10 to the 6 meters per second. Right? How does it compare to the speed of the light? You know, it's pretty fast, but it's less than 1%, less than 2%. Let's see here. Let's see. Compared to the speed of the light. Is that 1% of the speed of the light? I'm getting, calculate, 2% of the speed of the light. 3% of the speed, almost 3% of the speed of the light. It's very fast. Okay. 415. Let's see what else we have here. That's basically what you have to worry. Then you have to do that of the steering of the electrons. Okay, I already gave you the background for the steering of the electrons. You can look into that. We have applications in gel electrophoresis, especially in biological applications. We use a uniform electric field. Gel electrophoresis is a technique that uses applied electric field to sort biological macromolecules, proteins or nucleic acids. They have electric charges based on size. Okay? The molecules to be sorted are chemically treated, so they unfold into rod-like shapes, and so they carry a net charge in solution. So they have to be electrically charged, otherwise you cannot separate the molecules. The molecules are deposited to a gel matrix and an electric field is applied. The electric field is applied. It looks like a power supply. This guy here looks like a power supply to me, okay? This one in the back. So see the leads is your battery. Okay, an apparatus used to perform gel electrophoresis. The molecules to be sorted are placed in gel, in wells in the gel. Then the power supply, see, power supply is turned on, subjecting the molecules to a large electric field and make them migrate through the gel. Some molecules are heavier than the others, so the lighter molecules are going to get there earlier, right? Pulls the molecule toward one of the electrodes, depending on the sign of its charge. If no other force acted, the molecules would move with constant acceleration, but the force due to the gel opposes their motion. Yeah, there is some resistance there due to the gel. This force is similar to viscous drag. It's proportional to the speed of the molecules, where the constant of proportionality depends on each molecule to reach a terminal speed at which the electric and drag force balances, electric drag forces balance, smaller molecules move faster, right? Larger molecules move slowly. So after a while, the molecules are sorted by size. Oh, wait a minute. By size, yeah. Smaller molecules move faster. Okay, he didn't say anything about the mass. Yeah, larger molecules has more drag. The molecules can then be stained to make them visible. Yeah, people, they do that all the time in biology. They use dyes to stain molecules. Depend how the molecule interacts with the dye, they're gonna get a different colors. Okay, so here you go. Here is the molecules along the gel between the two plates, right? They are separated because they are moving at different speeds. Oh, they stay, okay, they stay with the same element. Okay, they all have the same color, okay? After electrophoresis performed, the fragments stained with ethidium bromide. They can then be viewed under ultraviolet light. You apply ultraviolet light, so it's just one color that they put in there, a single stain. Force and torque, okay, and you can look into that as well. I can do that for you next time. It's 420. Any questions about that? Okay, you look at that on your own as well. I will record the video on that too, so you can understand how the torque on a dipole works. Any questions? I have a office hours right now. If you want to hang out to ask any questions, feel free to do so. I'm going to stop sharing my screen, and we're done here. Let's stop my video. Stop it here. Let's see. I will